Hello everyone, I'm Gang Xiao, the main lecturer for this chapter. Earlier, we studied the structure of polymers and polymer solutions. Now we will move on to the next chapter, the thermal motion of polymers. First, please look at the three figures on the PPT. The first figure shows a bicycle tire. The second figure shows a girl's hairband. The third figure shows a plastic water bottle, for example, Mizone. They correspond to the polymer materials rubber, PMMA, polymethyl methacrylate, and PET, polyethylene terephthalate. Rubber, at very low temperatures, typically below 0 degrees Celsius, becomes hard and brittle. Polymethyl methacrylate behaves as a rigid solid at room temperature. It softens when the temperature rises above 110 degrees Celsius. Plastic water bottles should not be used for hot water. If the temperature is too high, they will soften, deform, and shrink. Now, let me ask you, at different temperatures, do the structures of polymers change? Clearly not. In other words, even though the structures don't change, at different temperatures or under external forces, the molecular motion is different. The physical properties also differ. These plastics perform differently at room temperature than they do at high or low temperatures. The same polymer shows different properties under different conditions. This reflects different states of molecular motion. These plastics can be used in different fields. It is determined by their structure. However, structure and properties cannot be directly correlated. They must be connected through the polymer's molecular thermal motion. A polymer's structure determines its mode of motion. The mode of motion of a polymer manifests macroscopically as its properties. Polymers with different structures have different properties. Properties are manifested only through molecular motion. Molecular motion is the bridge between microscopic structure and macroscopic properties. It is important to understand the mechanical states and thermal transitions of polymers. First, we should analyze the characteristics of the molecular motion of polymers. These features of motion arise from the fact that polymers are macromolecules. They are quite different from the small molecules we commonly encounter. It is a long chain. Only by understanding the motion of this long chain can we fully grasp a polymer's mechanical states and the transitions between them. The molecular motion mentioned earlier forms a bridge between microscopic structure and macroscopic properties. So, what are the characteristics of the motion of polymers? The thermal motion of polymers can be summarized in three aspects. First, the thermal motion of polymers is multifaceted. Second, the thermal motion of polymers is time-dependent. Third, polymer thermal motion is temperature-dependent. First, let's examine the multifaceted nature of the motion of polymers. Because polymers have long chain structures, their molecular weight is not only high, but they also exhibit polydispersity. In addition, they may have different side groups, as well as branching, cross-linking, crystallization, orientation, and copolymerization. These factors result in the multiplicity of motion units in polymers. In other words, the molecular motion of polymers also exhibits multiple modes. That is to say, within a polymer, there are various motion units of different sizes. These motion units include side groups, side chains, repeat units, chain segments, and even the entire polymer chain. What are side groups? They are substituent groups attached to the polymer backbone. For example, chloro groups, bromo groups, methyl groups, and ethyl groups. A branch is a side chain that extends from the polymer backbone. A repeat unit is the basic structural unit that makes up a polymer. A chain segment is defined when internal rotation occurs at a particular bond in the macromolecular carbon backbone. It affects the nearby repeat units. This causes them to move together with it. The collection of these mutually influenced repeat units is called a chain segment. It is the smallest unit capable of moving independently. It also defines the size boundary within polymers. We also studied molecular motion in physical chemistry. We call that Brownian motion. To align with the field of polymer science, We still refer to the motion of the entire polymer chain as Brownian motion. Because polymers have very large molecular weights, we also refer to them as large-scale motion units. That is, larger than the size of a chain segment. The motions of other repeat units or chain segments are called small-scale motion units. The motion of these small-scale motion units is called micro-Brownian motion. Large-scale motion includes the overall motion of the polymer. As a whole, the polymer shows center of mass translation and motions within crystalline regions. Polymorphic transitions, motions of defects in crystalline regions, and local relaxation modes within crystalline regions. Forms of small-scale chain segment motion include internal rotation of carbon single bonds in the main chain. This allows parts of the polymer chain to move while the molecule as a whole remains stationary. That is, with the chain's center of mass unchanged. Some chain segments move relative to other chain segments. Motion of repeat units, motions on a scale smaller than chain segment motions. Motions of side groups. Side group motions are diverse. For example, rotations, internal rotations, and end group motions. Why do polymers show different properties at different temperatures? Because at different temperatures the motion units differ. This leads to differences in polymer properties. Let's briefly summarize this section. The study of polymer motion provides a bridge between microscopic structure and macroscopic properties. Polymer motion has three main characteristics. 1. Diversity, manifested in different motion units. 2. Large-scale, motion of entire polymer chains. 3. Small-scale, motions of repeat units, chain segments, and side groups, etc. Alright, everyone, this concludes this lesson. See you next class.